Hi everyone. Welcome to our talk about migration in Spark. I'm Tomer Koren. I'm a senior software engineer at Microsoft. Together with me is Roy Levine, which is a senior researcher in Microsoft. Both of us are working on a product called Azure Security Center, which is mainly focused on threat detection in the cloud. So today we have several goals that we're going to speak about. The first one is tell you about the migration that we did recently for our production system. We migrated our big data platform from legacy technology to Spark. The second goal will be to present a methodological approach how to accomplish this migration task. And the last goal is to explain about the measuring quality, how we measure the quality, how we optimize the performance, and what is the definition of done. So a little bit background to get a little bit context about Azure Security Center and threat detection in the cloud. So as you may know, a lot of organizations had their servers in the on-prem, and recently they start migrating all this load into the cloud. Now, as you probably know, in the internet, there are bad people, bad attackers that constantly attacking the resources and trying to do brute force attacks, trying to steal data. And for that reason, we wanted our customer to be safe. We have the product called Azure Security Center, which protects the load both in the cloud and both in the on-prem system. Now, specifically, the product, one of the key ideas to protect customers is to notify them upon security threats. So one of the components that we're responsible of is to provide some detection analytics that whenever there is some attacks, we will notify the customer in alerts. We can notify customer alerts about incoming brute force attacks, SQL, brute force, and a lot of other threats. Now, the key engine for all those analytics is a big data platform. And in this slide, you see actually the detection pipeline backend architecture. You see from the left, you see that we are processing several data sources. There are also data sources at various sizes. The biggest one of them is contain around 4 terabytes of events per hour, which is a lot. We then process all this information and we created a second level of data we call process data. And then we have several detection pipelines. So some of our pipelines use use supervised models, and the component usually is a feature extraction model. We extract feature, and then we are classifying, we do some classification and then produce alerts. And other pipelines may be pipelines that are run anomaly detection. In those pipelines, the structure is more complicated. We need to calculate state every hour and then store the state and then eventually create a long time series based on previous states and then run the anomaly detection engine and then send alerts. Some of the components in this diagram are reusable. For example, alert publisher is a component that is used both by the anomaly detection and the classification-based pipeline. Okay, so now that we know about the general pipeline, let's talk about the challenges that we are facing during the migration between the legacy platform to Spark. So you may expect a migration process to be a straightforward task, but in reality, things are starting to become a little bit complicated. So what are the challenges that we are facing? So when we migrate different technologies, in our case, Cosmos, which is some flavor of Hive, to Spark, first of all, you have to maintain the semantics. You need that a given input, on a given input, we will have the same output on both of the systems. In addition, we need to follow some real-time constraint. Our system run on the hourly, some of the pipeline run on an hourly basis, some of them run more time, and we need that every pipeline will finish in time. We cannot let pipeline run more than 60 minutes if this is an hourly based pipeline. And the Third challenge is, of course, cost. We cannot just spend as much as we want. So let's focus on the challenges. So as for semantics, the first thing that you're going when you start to migrate code is to rewrite the UDF. In our case, most of our UDF was written in C#, and we had to translate them to Python. In addition, we have to rewrite all the transformation. In our scenario, our legacy transformation was written in USQL, and we had to convert them to PySpark. This, of course, may lead to a lot of bugs, as we discovered. Now, as for an example, we have here two examples of transformation. One is written in USQL, and one is written in PySpark. You can see that their two languages are totally different, and some activity may require more code than the other. Now, another thing that I want to mention here, for example, is the order by. As you can see, both of the codes use a window function, and the window function is an order by expression. Because those are different technologies, in some scenarios, when the timestamp is, there are several records with the same timestamp, the selected order, in this case, we use the row number, each row may get a different row number based on the platform. So in USQL, we'll see a different number, and also in PySpark. This could lead to a problem because in some of our features, we used to select several like top 5 or top 10, and then the rows that are being selected are different. This affects our semantics. Another point that I want to mention is different data types. In Spark, we are using, of course, Python data types. In our previous system, we used C#. In this table, you see two basic operations that we did between two numbers, number 1 and number 2. In some cases, the number was null, in other cases, 0, and we tried all the combination. You can see that in Cosmos, while in Spark, you see a lot of nulls in scenario when the number is null or division by 0. In Cosmos, we get different types. Especially, you can see the infinity and minus infinity. This change is very important because later on the pipeline, usually in the case of infinity, we replace the number with this infinity symbol with I number, and also for the minus infinity when we replace it with low number. When we get null, we cannot decide what we're going to do, and then there is a chance for difference. And again, because we are changing a platform, the machine learning libraries are also going to change. If in the Cosmos, the other platform, we use something that's called TLC, in PySpark, we use something called sklearn. So there is a difference in algorithm also. Now, another thing that we had in our scenario was a change in the schema. In the legacy system, for example, we had a scenario when we described a network IP connection between source and destination. In this case, we also tried to map whenever we knew to allocate the host name for the specific IP, we had a field called host name, and another field that is called that mentioned if the host name belongs to the source IP or if it belongs to the dest IP. Because we only had one field for the host name, in case both sides, for example, in this example, both the source and destination, we had the mapping for the host name, we had to duplicate the row, and one row put a true value, and the second we had to put a false. Now in Spark, we decided to allocate two fields for the host name. So you see that for the scenario I just mentioned, we have two mapping in one row. So in overall, you see that instead of 3 rows in the legacy system, we have 2 rows in Spark. Another thing that is important to mention, we also add some field called host ID. Host ID and host name was related to each other, and we decided to skip it in Spark. But later, when we did some investigation, we realized that in 1% of the time, there is a mismatch between the host ID and the host name, which also led to semantics problem. And again, there are the real-time constraints. Because we have several pipelines that are run on an hourly basis, and some of them run with a lot of data. We need to make sure that once we implement them, the overall runtime will be less than 60 minutes in order to avoid accumulated latency. And you may think of that some of the challenge can be mitigated by adding more and more and more server. It's maybe true, but when you add more and more server, the cost increase dramatically. And then the manager is not very happy. So you need to stay on some level on predefined threshold. Specifically on our system, because we migrate the existing system, we had a predefined threshold that we couldn't just expand more of it. Now Roy is going to introduce the formulation.
Thank you, Tomer. So I'd like to formalize the problem a little bit and formalize our solution. So if we go back to this pipeline, this detection pipeline that Tomer presented earlier, we can see that we have many different detections. And one way to go about it is to look at each detection as one big monolith and then try to migrate that. But that's not really going to work because the detections have a lot of code, like we're talking thousands of lines of code, complex code. There's no real way to just rewrite this entire detection and then compare the results and hope that they will be the same. So instead of doing that, what we did is that we split the, we look at each detection and see the components it's built out of. So these components contains like sub parts that the detection requires, like feature engineering, like classification, state management, stuff like that. We can take each one of these components and then migrate them separately. So if we take a Cosmos component, we want to create an equivalent Spark component. And then what we need to do is we want to thoroughly test these components. So to make sure that we don't have any problems, what we do is that we feed in the Cosmos data inputs into the Cosmos component to generate the outputs. We can then take those same inputs and feed them into the Spark feature engineering in this case, generate the outputs and compare the outputs. Unfortunately, it turns out this is not that simple because as Tomer mentioned earlier, the schemas don't match. So there's going to be a schema mismatch. There's no way to just take those inputs and feed them into Spark. So what we need to do is we need a translator that's going to translate the inputs into the Spark component and then produce the outputs. And then we can compare the outputs using some kind of a comparator function that we also need to write correctly. This way, we can validate each of the components to make sure that they pass our tests and they actually produce the same semantics. So how do we manage this, all of this together? So we have many components, each from a different detection. Some components are reused. And what about the connections between these components? So they're connected in some way. You can't just test each component separately and hope everything is going to work, because you need to connect everything together and then test everything together when it's connected. So that part requires validation, and also it requires us to specify how to connect the different components. So to manage all that, we introduce a framework that we used for this, a framework which is called SciFlow. So I'll explain about this framework. So we begin by introducing a multi-transformer. A multi-transformer basically is going to represent a component, a single component. This component is going to receive as input a multi-data item. The multi-data item is basically just a set of data items. Each data item can be either a data frame or a model that was pre-trained and is being fed into the multi-transformer. Then, in turn, this multi-transformer is going to generate a new multi-data item. And this new multi-data item can then be tested accordingly to make sure it's the same as what we had in the Cosmos component. Now, we can connect the different multi-transformers with one another to create basically a DAG, a directly acyclic graph of multi-transformers. This could represent an entire detection. The detection itself can also receive the multi-data items and produce new multi-data items. So in fact, when we use composition, the detection itself is also another form of multi-transformer. And the idea of a DAG or a directly acyclic graph is not new. Spark uses it as well. But Spark uses a DAG on very primitive types like operations such as select, join, filter, and so on. Here we're using the concept of a DAG over higher level objects, or basically objects that have a sense in a higher level of abstraction. Things like feature engineering is connected to model training or model prediction. And that way, when we look at this DAG, we can make sense of it and understand what it does in the logical sense. So our multi-transformers can also be stateful because some of our components actually are based on historical values, like the anomaly detection that Tomer mentioned. It needs to read data from a previous slice and then compute a new slice, and which it will read in the next iteration. In that way, it's stateful. Okay, so I presented SciFlow, and let's look at what would happen if we just wanted to do this using many notebooks. Just a simple notebook approach in Databricks, create many notebooks, maybe one notebook per detection, and then run that. So first, in terms of deployment, how would you deploy that? You would need to deploy these notebooks in some way into the cluster, maybe one cluster or multiple clusters. With SciFlow, all you need to do is just take the DAG that you created and deploy that into the cluster. It's easier to do. You can unit test because SciFlow, you're developing everything inside an IDE. You could do unit testing in a rather simple way, just the way unit testing is done in natural programming. You create standalone Spark and run your unit tests. There is shared utility code, which is easier to manage using a repository versus when you need to upload a wheel file and then use it in notebooks. I think the most important thing that SciFlow provides is the structure, the way the different components are connected with one another. This in SciFlow is very simple. You could even see it using the UI that Spark provides, whereas with notebooks, you need some sort of framework to say how these different notebooks connect with one another, or how the flow in one large notebook actually works. It's difficult to understand code containing thousands of lines. Finally, in terms of typing, so you don't really have any schema checks when you connect different notebooks in some kind of custom way. Whereas in SciFlow, every edge is being checked by the SciFlow engine to make sure the schema is matching properly. So it turns out that when we want to validate components, it's not as simple as you could originally think. So you have this output of Spark and output of Cosmos, and you want to compare them. So you want to write this comparator, which is going to compare them. But then there are a few challenges. So recall the few challenges that Tomer presented. So for example, some of the ML models or legacy models, which we don't have available for us in PySpark. This is C# code. We can't run that inside PySpark. So the models are going to generate slightly different results. It doesn't mean that there is an error. It just means that the results are not entirely the same. Furthermore, some of the semantics are not completely deterministic, like for example, selecting top K, where some values could be equal, as mentioned. Some schema translations could result in results not being always the same, and some randomly generated UUIDs also cause a problem when you just want to syntactically compare results. So how do we deal with all this? And how much should we really spend in this comparator logic to make sure that the results are really, the parity is full and accurate? So we try to achieve high parity, but if the parity is not perfect, we could go to the final output results and see. So we have the alerts generated by the legacy component by Cosmos and the alerts generated by Spark. We can look at the resources that we are generating the alerts on and compare them to see if they're going to be the same resources, then it means that despite our results not being syntactically the same, in terms of the alerts that we produce, we're good, we're fine, we could mark that as done and move forward. When the results are not perfect, we can use these measures like Jacquard similarity, precision, and recall, and then decide based on these values. So for example, for some detections that are known to be a little bit more noisy, we can focus more on precision than on recall. So for example, we could set a higher threshold to make sure we have high precision, maybe at the expense of some recall. If the values are low, are just too low, no matter what the threshold is, then we need to maybe continue to hunt bugs that may still exist in the code.
Thanks, Ray. So now we talked about the metrics. Let's talk about tuning performance. So we checked, then we verified that our two data streams are equal and the correctness threshold was achieved. But what about the running time? So in this case, in these steps, what we're going to do is just measure the running time on an actual data. This is the next step. So we just insert the real data, the real new data into the pipeline, and then start to measure the running time. Now at the beginning, there were some pipelines when first time we run them, and suddenly we saw that it takes too much time. And some of the times I had to go to sleep and then woke up in the morning just to realize that the pipeline, the overall time was taking 14 hours, which is way above our expected threshold. So in this case, what I had to do is start to debugging the problem. Now, since it's very hard by looking at the actual physical graph to understand where exactly the component that calls for this high latency, and there is not a tool that I know of for providing profiling over file code, we had to debug each component separately. So for example, let's assume that we want to start investigating the feature engineering part. So what we are going to do here, we are trying to find the culprit. So what we'll start doing is first divide the feature engineering part into sub-transformation. We will select several transformation, group them together into logical group. And then what we're going to do is output the result, materialize the result into disk. Now, let's assume that the first check of the first part was taking us 20 minutes, which sounds acceptable for us based on our expectation. And then we continue on the second part with the second group of transformation. In this case, we suddenly saw that we have 13 hours. So in this case, we managed to find the problematic area. Now that we found the problem, we need to start solving it and start working on some optimization of this component in order to reduce the running time. So what's worked for us best for tuning parameter was several things. First of all, for example, in the anomaly detection, we had a pipeline that aggregate a lot of hourly slices and then read them all in a resolution of 1 day or 1 month. Let's assume that we have a lot of hourly slices and we read them at 30 days of hourly slices. There will be a lot of files because each hour has a lot of partition and the number of total partition number files to read is very big. So what we decided to do, we created a daily process that aggregate the hourly slices into one daily stream. So we add a daily aggregator, and then we produce once a day, we produce the daily stream, and this led us to improvement in some of our analytics. Another optimization that worked best for us is to modify the default partitions of the cluster. Let's assume that our cluster has 300 cores in total. So we decided to define the partition level based on the number of cores multiplied by 3. So in this case, for the cluster I mentioned, it will be around 1,000 partitions. Those partitions are good for a shuffling partition and also for the general partition. Another thing that you're going to use is to use the broadcasting when the UDF had a large signature and was used frequently. In some of the cases, we had several UDFs that are run once at a time after another. And once we broadcast the UDF, we saw significant improvement. Now, another thing that was very good for us was cache. Some of the data frames that are being used more than one time, it is very wise to to cache them. But be aware, in the beginning, we start to cache a lot of data frame and we didn't free the memory. And what happened, we got a lot of error for memory failure and spill error, and it was very hard to debug them. So eventually what we did, we limit the number of cache. And in addition, we used unpersist. We removed the data frame immediately after we use them, and we don't need them anymore, just to free the memory and avoid of memory failure. So this was the tuning performance, and now let's summarize our talk. So in this talk, we present the general challenges that usually we're facing when we come to migrate large-scale big data pipeline from legacy technology into Spark. Let's remember the challenges. The challenges were preserving the semantics, real-time constraint, and of course, costs. In addition, we introduced SiteFlow, which is a framework we use to increase the usability and avoid connectivity bugs. This allows us to separate the problem into separate components and achieve good progress in the migration. In addition, we talked about different validation strategies, how to compare the data. And at the end, I talked about the overall time reduction by optimization. And once you optimize the code, you can use less stronger machine and which reduce the overall costs of the system. So this was the lecture. I hope you learned a lot and we managed to transmit the message, and we very enjoyed, and thank you everyone for your time.